Let's get looking at chapter 6 now. This is an important chapter that students don't seem to understand very well. Well, at least college students don't seem to understand it very well. In section 6.1, we don't really do any geometry, we just do some algebra. And the first thing is to make sure we understand what we mean by a ratio. And basically, a ratio is just an ordered pair, an ordered pair of numbers thought of as a fraction. So generally, it's thought of as fractions. For instance, I could write this, and then we would say this is 6 to 2, and you can think of that as a fraction written this way or written that way. Okay, you could reduce it. As a matter of fact, generally we do reduce it, but we would reduce this down to 3 to 1 or 3 to 1 this way, but not down to a single whole number. In other words, it must always have some sort of denominator with it. Don't think of it as 3. Think of it as you're comparing two objects. One of them is 3 and one of them is 1. There are ratios you may already be familiar with. One ratio, geometric ratio, is slope. Remember what the slope is? It's the change in the y's over the change in the x's. Okay. Another ratio, geometric ratio you might be familiar with is pi. It is the ratio of the circumference of a circle to its diameter. Okay, okay, so let's do a little cheap example here. Represent this as a fraction in simplest form, 82.5 to 16.5. We'll write it as a fraction. Okay. Now, if I'm reducing a fraction, I don't have my calculator with me. I don't like having decimals in it. This is the same as 825 over 165. And that's a little bit easier to reduce, perhaps, because that's 5 to 1. Now, a proportion. Proportion is merely an equation or an equality of ratios. So it's something of this form. A over B equals C over D. When you're looking at a proportion, these positions have names. And it might not be something you've heard before because it's a little bit old-fashioned. But A over B, the fraction A over B equals C over D. The number A and the number D are called extremes. And the two other numbers, B and C, these are called the means. Now that's really rather artificial because this is just an equation, so I could certainly rewrite it as C over D equals A over B, and now the extremes are B and C, and the means are A and D. So it just kind of depends on how it's set up here. But that's somewhat old-fashioned, but notation. The book uses it a lot, though. So when you're solving a proportion, there's one standard thing to do, and this is what it's called. It's called cross multiplication. And if I had my way, that phrase cross multiplication would not exist. You can call it that if you want to. I'd really rather you didn't, and I think it's kind of something you probably shouldn't teach your students, but somebody's going to teach them that anyway. So what this is, and is that A over B equals C over D if and only if the product of the means equals products of the extremes. That is, A over B equals C over D if and only if AD equals BC. So the idea is A times D equals B times C. And that's why it's called cross multiplication. Look, all you're doing is you're multiplying on the top by B over D so that it cancels on the left and you, excuse me, by BD. So that the B's cancel on the left, you have AD, and the D's cancel on the right, and you have BC. So I really don't think it should have a brand new name. As a matter of fact, an old professor of mine called this the means extremes product property. He didn't call it cross multiplication. But you're just multiplying, using the equation, the multiplication property of equality. Okay, now let me just go with a few reasons why I don't like cross multiplication. As I said, one of them is it's not anything special. It's just multiplying both sides by a single number. Okay. So don't give it a new name to make it sound like it's something exotic. Sometimes cross multiplication is not the way to go. For instance, if you're solving something like x over 14 equals 9 over 7, then cross multiplication would say take x times 7, and that should be 9 times 14. Okay. But that's a stupid way to work this problem. If you want to solve this, don't multiply by 14 and 7, just multiply by 14. And the 14s will cancel, and you'll have x is 14 times 9. 9 times 14 over, whoops, 9 times 14 over 7, and the 7 goes into 14 twice, just get 18. So all you need to do is multiply by 14, not 14 and 7. Also, the reason I really, really don't like it is what students do with it. Let's suppose we had this particular fraction multiplication problem. This is not an equation. It's multiplying fraction 3/10 and 35/18. Okay. Now what you would likely do in a situation like this is, at least what I do is, well, I think 3 goes into 18 6 times, 5 goes into 10 twice, and into 7, 35 7 times. So you get, let's see, a 7 on top, and a 2 times 6 is 12 on the bottom. Now, ask students what they did there. They're going to say they cross multiplied. But no, they didn't cross multiply. They merely reduced fractions. So this phrase is used incorrectly many, many times. It implies that something very different and special is going on when you've got an equation like this. And the truth of the matter is, it's nothing special. So I don't like to use that term. Okay. Now on this one, determine if this is a proportion. Now what they have in mind on this is basically to do the what we're not going to call cross multiplication. But if this times this equals that times that, I'm going to go fall back on what my old professor said. If the product of the means equals the product of the extremes, so let's take 4 times 2 times 96. If that's equal to 0.9 times 289, then the answer is yes. Well, 4 times 2 times 96, 4.2 times 96 is, let's see if I got this right. This is, wait a minute, the wrong spot. Let's see what we got here. 4.2 times 96 is 403.2. I'll write that. And let's see what the other one is. 0.9 times 289. I don't think this is going to be the same. 260.1. These are not equal. Proportion is an equality. If this is not an equality, then that's not a proportion. Okay, now we have some equivalent forms of the proportion. On the left side, A over B equals C over D, our standard sort of proportion. And you can move some things around. In other words, exchange the extremes, okay, or exchange the means, or invert the ratios. Okay. What I'd like to do is actually prove another form of this proportion here. By the way, I don't think these are any things that really need to be memorized. If you've got a proportion and you need to rearrange it, well, all you're doing is multiplying the top and the bottom by something, or multiplying through by something, or something else. Okay. Now, number 30, if A plus B over B equals C plus D over D, then A over B equals C over D. Now, I know what they want on this problem. They want me to do the means extremes product property, okay, which I'm not going to do. I'm going to rewrite this. Remember what fractions mean. If it's A plus B is the numerator and B is the denominator, then both A and B are divided by the denominator B. Same thing over here. C plus D, this denominator D goes underneath the C and underneath that D. So what we get is, if this is true, this is true. If that's true, then A over B plus 1 equals C over D plus 1. Okay. And I can subtract 1 from both sides because we know the addition property of equality. Then I get A over B must equal C over D, which is what I wanted to get. So you could do this by cross multiplication. We said it means extreme product property, or you don't have to. Now, let's take a look at an example here. This is number 43. Oh, let me back up a little bit here. The book actually does something stupid. And he does stupid things every now and then. We all do stupid things every now and then. But if you look at example 6.5b, and this is page 301, they want you to solve the equation x over 7 equals 31 over 42. And what do? They take 42 times x equals 7 times 31. Now that's stupid. If all you need to do is to get at x, then why don't you just multiply both sides by 7? Then the 7's will cancel and you'll be left just with x. You won't have to do anything else with it. And let's see, this is 7 over 1, and 7 goes into 42. 6 times you have 31 over 6. If you do it this way, you've got an extra step in there. So if I see someone take a problem like this, x over 7 equals 31 over 42, and do this to it, then I tend to think they don't exactly understand what it is they're supposed to be doing. You're supposed to isolate the x, so you don't need to move the 42, you just need to move the 7. Okay, now let's work on number 43. For the tax year 2004, the IRS audited 65 of every 10,000 returns. Okay. This sentence gives us a ratio, 65 over 10,000. Here this is number audited out of the total. Okay. Part A, a community has 34,000 people that filed returns. How many were expected to be audited? If this ratio works everywhere, then the overall ratio, 65 out of 10,000. Okay. Oops, getting ahead of myself here. Let's identify this. Okay, we'll call that X. X is the number that we expect to be audited. If this overall ratio holds true, then the ratio in general that's audited should be the same as the ratio for this particular community. Okay, so don't cross multiply. No. Just multiply and left everything through by 34,000. Because when I take the right side multiplied by 34,000, it's gone. Okay. Then I take the left side and multiply by 34,000. Let's see, I get 221 equals X. Okay. Now, let's see what happened in 2003. In 2003, only 57 returns per 10,000 were audited. How many more of the 34,000 returns would be expected to be audited for 2004 than for 2003? Okay, so this is 2003. 57 out of 10,000 is the overall ratio that's audited. And this is going to be some number, I don't know. Y over 34,000, where Y is the number in this community audited in 2003. Okay, so we multiply both sides by 34,000. And we get that the number audited should be 193.8. So about 194. Okay. And so that's how many would have been audited in 2003. So we wanted how many more in 2004. So there should be 221 minus 193.8, 27.2 more. Well, you're not going to audit 0.2, so 27 more. Can't read that. Or maybe 28 more. Okay, a few terms here. I have two numbers, A and B. The arithmetic mean, the ordinary old mean, it's the ordinary old average. Add them up and divide by 2. Arithmetic mean equals ordinary average. Geometric mean is you multiply them and take the square root. So it's the square root of A times C, whereas the arithmetic mean is the average, the ordinary, the usual mean of A and C. Okay, here's a little theorem here, theorem 6.3. If A over B equals B over C, then B is the geometric mean. Oh yeah, it's also sometimes called the mean proportion. But from this proportion, mean, remember these guys were the means. These are the extremes, so the means here, that's why it's called the mean proportion. Okay, and the proof is something like this. If we do the means extreme product property, otherwise multiply everything on both sides by BC, we get A times C. And over here, if we multiply by BC, the C's cancel, equals BB, so AC equals B squared. Hence, that's what that's supposed to say. If we take the square root here, equals B, so B is the geometric mean. Now, there's one particular form of a geometric mean that's got special names. It's called the golden mean, or the golden ratio, the golden proportion, there's several terms about it used for this thing. It's also called the divine proportion. Okay. It is the number, use the lowercase Greek letter tau. Okay. And to find tau, you solve this proportion. Tau over 1 equals 1 over tau minus 1. And multiply both sides by tau minus 1. It's equal to 1. So tau squared minus tau equals 1. Tau squared minus tau equals 1. So tau squared minus tau minus 1 equals 0. Quadratic formula says tau equals negative of b. You add or subtract the square root of b squared minus 4 times a times c all over 2 times all over 2 times a. This is 1 plus 4. So it's 1 plus or minus 5 over 2. Okay. If we're looking at the positive root, and generally when you do ratios and proportions, we're talking about positive numbers here. The positive root of this is 1 plus the square root of 5, all divided by 2, and that is the golden mean. It's used a whole lot. As a matter of fact, there was talk about it being some sort of the Greeks felt it was some sort of mystical proportion, and so they designed a lot of their buildings based on that, and that is somewhat true. It also shows up in some very, very interesting spots, and I've got a few problems planned for you to work using that, but we have to get another section or two done in the book. But for right now, that's it for section 6.1.